In this video, we're going to be learning about the experiment conducted by Ernest Rutherford, who set out with the goal of seeing whether J.J. Thomson's model of the atom was indeed the correct structure. In the previous video, we explored how J.J. Thomson believed that because positive and negative charge naturally attract to one another, that the electrons, which are negatively charged, and protons that are positively charged would be found together inside of a single nucleus, and that there wouldn't be any particles outside of this. So Ernest Rutherford set up a rather ingenious experiment that could demonstrate whether Thomson's hypothesis was true. The first thing that Ernest Rutherford did was collected a number of radioisotopes, which are atomic nuclei that are unstable and therefore release radiation. And the specific form of radiation he was interested in was alpha radiation, because alpha particles are the largest particles of alpha, beta, and gamma particles emitted when a radioisotope breaks down. And then Ernest Rutherford put these radioisotope samples into a container made entirely out of lead because of its high density. Now, because of lead's density, its atoms are very, very close together within its structure, which otherwise prevents radiation from being able to escape from a container made of lead. This is why when you go to get an X-ray at the hospital, they make you wear a vest made out of lead so that radiation doesn't penetrate any parts of the body that you don't want to be exposed to X-rays, because radiation is carcinogenic. Now, we can see that this lead container only has a single hole here, which focuses all of the radioactive energy into a single beam that Rutherford pointed at a piece of golden foil, which is basically like aluminum foil, only with gold instead. And gold was used firstly because it's easy to hammer down into a flat sheet, and also because gold, like lead, has a very, very high density, which makes it interesting to study when exposed to radiation. And around this, we have a detector screen, which it has the ability to detect whether any radiation is able to pass through. So if radiation were able to pass through, that the alpha particles that pass through the gold foil would be detected on the other side of the gold foil by this detector screen here. So in terms of what Ernest Rutherford believed was going to happen, he believed that the alpha particles would be able to pass straight through the gold foil like this. Now, in order to understand why, you'd actually need to ask a particle physicist about why alpha particles, which are basically helium nuclei, can pass directly through the atoms of gold foil, including the nuclei. But generally, when we get to the level of the nucleus, what we commonly understand as the laws of physics don't really make any sense, except for people with a strong particle physics background. Now, this was assumed to be the case because Ernest Rutherford assumed that the positive and negative charge within the nucleus would cancel each other out, because an atom would have the same amount of protons as it would electrons. However, when Ernest Rutherford conducted this experiment, what he saw was actually quite different, because as we know in our modern understanding of the atom, the nuclei and the electrons are actually physically separate from each other, which means if we take a positively charged alpha particle here, this alpha particle would be repelled away from the positive charge of the nuclei in gold foil. And depending on where the alpha particle beam hits, this would determine the direction of the repulsion of the alpha particle based on the angle that it hit the gold nuclei in. For example, if an alpha particle passed by here, the repulsion would deflect the alpha particle in this direction here, whereas if an alpha particle hit the gold nuclei right dead on, it would more or less be reflected directly backwards like this. So rather than the alpha particles passing directly through the gold foil, which is what Ernest Rutherford predicted because he assumed that all of the positive charge and negative charge would cancel each other out in the nuclei, what Rutherford actually saw was something like this, where not only did the alpha particles pass through the gold foil, but they also were deflected in seemingly completely unpredictable directions, which led Ernest Rutherford to two conclusions. Number one, that most of the atom is actually empty space, and this is one reason why alpha particles are able to pass directly through, because the nuclei of an atom actually represent a very, very, very small percentage of the overall volume of the atom, and this empty space, Rutherford concluded, meant that electrons and the nuclei of the atoms that contain the electrons are actually separate, and the nucleus must be positively charged because it is this positive charge that caused the deflection of alpha particles because of the repulsion between the positive charge of the alpha particle and the positive charge of the nuclei, and this would not be possible unless electrons were found outside of the nuclei, so the deflection of alpha particles in seemingly random directions allowed Rutherford to make this conclusion here. So the conclusion that Rutherford was able to reach is that Thomson, while having a seemingly logical prediction about the structure of the atom, was fundamentally incorrect. But unfortunately, Ernest Rutherford had no idea about how the electrons were organized outside of the nucleus, and it would fall to one of his successors decades later, a Danish physicist by the name of Niels Bohr, to come up with a third experiment that would ultimately determine the basis for our modern understanding about how electrons are organized in the nucleus, and that will be the subject of the final video in this series.